Hi everyone, I am Ceren Deveci and I am going to present the susceptibility weighted imaging technique for the EEE 574 course term project. First of all, before I start with the susceptible weighted imaging, I would like to mention the black blood angiography. In order to make a black blood angiogram, there are several mechanisms that can attenuate or eliminate signal intensity from blood. As in our method, susceptible weighted imaging, one can use the intrinsic T to start shortening of the deoxygenated blood to produce high spatial resolution black blood MR venograms. So susceptibility weighted imaging is actually a new type of contrast in MR imaging. So it is quite different from the spin density T1 or T2 imaging. SWI uses a fully velocity compensated three-dimensional RF spoiled high-resolution 3D gradient echo scan. And this method exploits the susceptibility differences between the neighboring tissues. And in order to manifest this contrast, the signal detects substances with different susceptibilities than the neighboring tissues, such as venous blood, hemorrhage, or iron storage. At the end of the SWI process, 4 sets of images are generated: the original magnitude image, the half-pass filtered phase image, SWI image, and the minimum intensity projection over the SWI image. So, physical principles of the SWI, some or all of the following features: for example, high resolution 3D gradient echo imaging, full flow compensation in all 3 directions, thin slices to avoid signal losses, filtering of phase images to reduce unwanted field effects, creating a phase mask image, operating on the magnitude image with the phase mask, and taking a minimum intensity projection over neighboring slices. So before I start to the susceptible weighted imaging, one should understand completely the gradient echo scan. Like in any other imaging method, one should first create the transverse magnetization, and then RF pulses produced, as you can see here in the picture. So in order to create the transverse magnetization, first RF pulse is produced, which tips the longitudinal magnetization, partially or complete into a transverse plane. That depends on the tip angle, magnitude of the tip angle. And when this longitudinal magnetization is rotated about, for example, x-axis, it will create a component along xy plane, and that component is received by a receiver coil. And afterwards, the data are encoded both in the phase and the partition encoding directions. And this phase encoding direction is y direction, and partition encoding direction is if the rotation direction is the x-axis. So then the read gradient is turned on, and the data are sampled in the meantime. After this, RF spoiling is applied so that no transverse magnetization component remains before the next RF pulse. So the key point of this susceptible weighted imaging is measuring the local magnetic field variations, which leads us to the amount of the phase change. So the measuring local magnetic field variations can be important of tissue properties, to improve sequence design, to observe effects in the body that can change the local field. So here the phase change as a direct measure of the magnetic field variation, and the simplest approach to measure the magnetic field variation is to acquire a gradient echo image with instantaneous sampling, so that there are no phase variations induced by motion and no distortion. Then the formulation is shown here. Gamma is the gyromagnetic ratio, delta B is the field variation, and T is the echo time. And we can rewrite this equation with G and delta X. Here G is the geometric constant, which depends on the object. This delta X is susceptibility difference, but I have to define susceptibility for you. Susceptibility is one of the measures of the magnetic properties of a material. Susceptibility indicates the magnetic response of a substance when it is placed in external magnetic field. So as a result, the phase change depends on the local tissue susceptibility. And for this imaging technique, only diamagnetic and paramagnetic substances are considered. So as long as our magnetic field variation is small enough for a given echo time, the phase change is in the interval of minus pi and the plus pi. So if the value goes above pi, it wraps to minus pi, and inhomogeneities in the magnetic field cause a low spatial frequency dependence, which means the phase may vary over the image and the phase may appear different than the actual phase. This difficulty can be avoided when either we perform phase unwrapping or we apply a high pass filter. So the effect of high pass filter can be observed in this image. In image A, raw phase image is shown, and then when we apply the high pass filter with different sizes, then we can reasonable image, and it can be quite illustrative. So in order to enhance the contrast of the susceptibility weighted image, the phase mask is designed by suppressing pixels having certain phase values. So as you can see, for the negative phase values, we suppress the phase, and for the positive phase values, the phase mask function equals to 1. This masking function is illustrated in the picture below. Afterwards, the magnitude and the phase data are brought together as a final magnitude SWI dataset by multiplying the phase mask image into the original magnitude image. As you can see, the phase mask function is multiplied with the magnitude image more than one time, and this creates a new image with a different contrast. So this number of multiplication n is estimated as 4 in order to optimize the contrast and noise ratio of the SWI image and to produce a series of SWI data that can be used in diagnosis. So here you can see all of the processes before. In this picture, A shows the unprocessed original SWI magnitude image, and B is the half-pass filtered phase image. C is the processed SWI magnitude image after the phase masking process when M equals to 4. So in D, E, and F, you can see the dark hypointense ring around the vein cross sections. The contrast is getting better when we examine the photographs from D to F. So both magnitude and the phase information are essential for proper tissue characterization and the creation of an SWI image. And combining phase and magnitude image ensures the detectability of the signal intensity changes coming from both T2 and the susceptibility differences between tissues. After this phase making process, the SWI data are often viewed by using a minimum intensity projection over 4 or more images. MIP is useful to show a projection over multiple sections, and this provides a larger coverage of the veins in a given area. As you can see here in the image, you can observe the difference between the photograph A and B, and in photograph B, the veins are picturized in a detailed way.